All right, we're going to look at gyroscopes today. Gyroscopes are some of the most perplexing applications of classical physics that we have around, and so my goal is going to be to try to make them a little more understandable. We're also going to see that there are some applications of the torque equation that can help us understand gyroscopes. And then once we understand them better, we are going to go ahead and try to look for a more physical description for why the gyroscope works. Now, if you take a mass and you hold it out like this, and it's not rotating, and that's the kind of perspective I'm trying to draw here, then we see that there is a torque that is going to make the system want to rotate like this. Okay, and so that's what we would expect. But what happens instead is that when we spin this thing, then we're essentially defying gravity. So it wants to turn around like this rather than fall straight down like that. So what we're going to try to do is explain why that happens. Now, if we use the idea, we've got two different expressions for the torque. We've got the expression where it's equal to r cross f, but we also have another expression for the torque in which it's equal to the derivative of angular momentum with respect to time. Now this comes straight from the fact that if L is equal to I omega, then dL dt is equal to first times derivative of the second plus second times derivative of the first. Let's assume here the moment of inertia doesn't change. So that would be equal to just first times derivative of the second, I times d omega dt, where that's equal to I alpha. So that's equal to the torque. Okay, so we do have a torque working here, and that torque is due to the object having a torque applied to it. But then the question is, how is that affected by the change in the angular momentum? Well, if we have the wheel rotating round and round like this, so on the back side it's coming up, on the front side it's coming down, then the direction of omega will be this way, and since L is equal to I omega, L is going to be in that direction. Okay, now the torque we can get from R cross mg, or R cross F. So if we do that, we get a torque that is into the page. So that direction of the torque must be in the same direction as the change in angular momentum. So now if we look at this thing from a top view, so here we are looking from a top view, looking down on this thing, then this thing is going to be in this position, let's say at time equals 0. Here's going to be the angular momentum pointing away. And then at some very small time later, it's going to have moved a little distance d theta, and now L is going to be pointed in that direction. Okay, so the fact that we have angular momentum in the rotating disk is manifesting itself by a torque which is going to happen in the direction of changing angular momentum. So if this is L initial, and this is L final, then this must be delta L. So delta L then is in this direction as it goes out to this new position here that is d theta. Okay. And so we can say then, if this is d theta, that d theta is equal to the sine of d theta. And it's also equal to the tangent of d theta, the small angle approximation. This is a small theta. By definition, it's the smallest theta you could ever get, right? So the sine and the tangent approximation are also valid. So let's use the tangent approximation here. That gives us d theta is equal to delta L over L. Or actually, this is really dl, if we want to think of it that way. Okay, so we have a change in the angular momentum then that's happening in the tangential direction because torque is equal to r cross f. And the change in the angular momentum must happen in the same direction as the torque, because torque is dl dt. So this is the change in angular momentum, this direction. That must be the same direction as the torque is being applied. And so it causes this non-intuitive change in the direction of the disk as it's rotating around and around in this horizontal plane. So from that we can get the precession frequency. And that's going to be equal to d theta dt. Okay, so this is an angular velocity, but it's also a rotation rate. And so this is the rate at which theta is sweeping around. And so that's going to be equal to d by dt of this expression, delta L over L. But that's just basically equal to dl dt over L. So our precession frequency then can be written as, well, dl dt though is the torque. So we can write that as the torque divided by the angular momentum. Now which angular momentum are we talking about here? Well, we're talking about the angular momentum of the disk. Because as this thing rotates, it also produces angular momentum about this direction. But it's a smaller amount of angular momentum. And then if there were no rotation, you would have angular momentum that is associated with the disk dropping. But here what we're assuming in this approximation is that the disk is rotating fast enough so that this torque that's caused by that term outweighs this torque and outweighs the changes in angular momentum that are produced by the vertical part of the disk. And so this is an approximation. Now the torque in this case, since the object is on a horizontal level plane as it moves, is going to be equal to the mass of the disk times g times the radius of that lever arm divided by L. Okay, so L then is I omega. So this is a different omega. This is the omega that's associated with the rotation rate of the disk. Okay, and so if this were a uniform disk, we'd make it 1/2 mr squared. But since it's a bike tire, right, that is rotate as it rotates. Here, let's make it go the other way. There, like that. Okay, so it's rotating this way. As it does that, the omega is the number of turns per second of the wheel itself. And this is related to the rotation rate of the precession, basically what we call the precession frequency. That is related to how long it takes to go all the way around once. Okay, so we can rewrite this then as big M GR divided by big M times little r squared times omega. So we can see then that if omega is equal to 0, we are out of the range of the approximation by which this relationship is valid. Because if omega is 0, we're dividing by 0, that would give us an infinite precession frequency this way, which is a nonsensical result. What happens instead is when this omega becomes small, there's a certain point at which the torque that's caused by it falling is larger than the torque that's caused by it being rotated like this. So at that point, we've left the point where this approximation is valid. And so omega here needs to be high. And for a high value of omega, we're going to get a low value for the precession frequency. So let's see if I can rotate this thing fairly slowly and see how fast it rotates around. This is our precession frequency. But now let's see if I can make this thing go faster. Now do you see that it's going more slowly? Now it's rotating around more slowly than it was before. And I'll be able to increase that frequency even more with some help at the end of this video. So now the masses cancel from this expression, and this just gives us GR divided by little r squared omega for the precessional angular velocity. So this is the rate at which this system, this is the angular velocity of precession. Now, is that all there is to gyroscopic motion? Well, no. There's quite a bit more. If you start this thing, say, in a position like this, a little more vertical, we have a precession that's happening in this direction, but you also, if you look carefully, will see that there's a nutation, which there's a little bit of a wobble happening in this direction. So as the thing goes around, it's not just a smooth curve, but instead, what you can feel is a little bit of a fluctuation. Okay, so you've got two different kinds of motion. You've got the regular precessional motion for a gyroscope as it rotates round and round like this. But then superimposed on that, you have a fluctuation of the height of this object. What is that being caused by? Well, that's being caused by an interaction between the gravitational torque pulling this way and the precessional torque, which is going that way. And so there's like a conflict between the two. And when the precessional frequency gets low enough so that it starts to interfere constructively with the rotational frequency, what you get is a wobble, and it tends to overshoot that wobble and go back and forth. And so that wobble is called nutation. So this is precession around this way. So that's a variation in this direction, but nutation is in this direction. So that's what's bringing it up and down. As it's going like this, it's going in and out, up and down. That's creating the nutation. Now for the Earth, instead of having a period of precession on the order of a few seconds, as is the case with the gyroscope, if this is the North Pole now, this would be the North Pole in about 26,000 years. So this would be the North Star here, right now. And then in 13,000 to get to its maximal point. And then to be back to this point again, it would be 26,000 to go through one complete cycle of precession, going round and round like this. The time that it would take is about 26,000 for it to get to this point, and then another 13 to here, another 13 to there. So this is 26,000 years from now, we'll have another North Star. But 13,000 years from now, we'll be pointed more at the star Vega. Although it won't be exactly our North Star. We're really lucky, by the way, right now, that there's a star that actually does point pretty close, about half a degree away from true north. That means that in 13,000 years, if we don't account for it in our clocks, it'll be 6 months later for the beginning of, so instead of being the beginning of spring on March, say 22nd or something, it'll be the beginning of fall. And the beginning of winter will be shifted to the beginning. But when they do their time corrections, they correct for that. So it actually stays the same. But if you just followed the position that the Earth's axis is pointing and then go around 26,000 times, it's going completely through this shift in the direction of the rotational axis, and it's back around to where it started from. While that's happening, the nutation takes about 40,000 years to go from 21 degrees to 25 degrees. Okay, so the tilt of the axis changes between max and min values of 21 and 25. Currently, it's at 23. Okay, and so what that means then is that it shifts like this, too. Okay, and so in the last 5,000 years or so, we've shifted enough from a higher angle to a lower angle so that the Sahara Desert has completely dried out. Okay, so that used to be lush places where civilizations were having a good old time. And then it got really dried out. They had to leave, and so that's one of the theories, and that is just by maybe a 1 degree shift in obliquity is all it took in that nutation to open up the whole Sahara and force people to either the Mediterranean, or it's thought a lot of people went to the Nile River, and that was the beginning, it is thought, of the Egyptian Empire many thousands of years ago, and then the pyramids and all of that happened. And so that's the kind of thing that can happen on the scale of the Earth. Now what about trying to understand, though, how this thing defies gravity? Well, let's simplify our thoughts for a second. We say, well, if I pull it this way, why doesn't it go this way? If it's spinning, why does it still go that way? Okay. Well, let's think of this thing from the standpoint of, now we could have a tension here, or normal force. This is mg. And so that's going to tend to make the system, you can see here the tension is pulling up, mg is pulling down. So both of those things are going to have a tendency, you would think, to make the system want to rotate that way. But what I would like to contend is that that has the same exact effect as applying a force here and a force there on the disk. That should have the same effect of rotating this disk as the torque does in rotating the disk. And so I'm going to put my forces here because I can't see what's happening with the gyroscope unless I look at those equivalent forces. And so if I look at those equivalent forces, then I can see what's happening. Now, before I try to show you what's happening with two forces that are happening, say with a disk that is rotating around and around like this. So it's going to go like this. And so this will be, let's say, the front side. This will be the back side. What I want to do is just point out something a little more basic to you. That is what happens when a mass is moving in a straight line with a velocity like that. And I apply a force this way. If I apply a force that way, does the object go straight up? The answer is, of course not. It still has this motion from its inertia from traveling in this direction. So as I push up on it, it starts to slowly change its direction more and more to the vertical. But it's still, you haven't gotten rid of that horizontal part of the motion. And so we already know that the direction that you push an object is not necessarily the direction that it's going to go. Okay, and so that's the case then with this disk. We're pushing this way, but the actual motion is this way. And it's related to this idea, but it's a little more complicated, you know. And that's why it is one of the most perplexing and misunderstood concepts in physics. Okay, so let's say that I'm pushing on here. Maybe this is a planetary orbit. And so as the planet goes around like this, I push on it a little bit like that. Okay? Because it's going around in its orbit. It gets to this point, I push on it there. Is it suddenly going to go to here? Is that going to be its orbit now? No. It's going to slowly change direction. And so what happens then is it slowly changes direction. You're pushing on it here, is that it's going to go, now it's not just going to go because I'm pushing this way as the object is moving around like this. It has a direction of the force that's perpendicular to the direction of the velocity vector at this moment. And so that's going to tend to push it, instead of it coming straight at us like this, it's going to go out like this. Okay? But it's going to take the rest of the disk along with it. Okay, so just to try to get the perspective a little better here, let's say this is where it is initially, as it's coming up, coming out at us here, then coming down. Then I push on it. What that's going to do is that's going to push it out into this motion, but it's not just going to go straight out like that because it has to still stay on the radius of the rim. And so it's going to have that net effect of being pushed out, just like a planet that's going around like this. If it's being pushed at this point, then that's eventually going to cause it to go around to some other value, and then if it's being pushed from the other side, then coming in from the other side, this force is going to push on it like this, and it's going to drive it out to this position. But this position, in terms of the rotational plane, has been rotated by an angle phi, this way. Okay, so I'm pushing on it this way. It's coming around and down. And then by pushing on it this way, that gives it a little more velocity in this direction, but it still has to travel around in the circle. While that's happening, this one is being pushed, and that causes it to, instead of following this original path, it's going to push it out to this new path on this side. Instead of going out like this, it has to stay on the rim. So as it stays on the rim, what that corresponds to then is a rotation from this position to this position. Okay, and so this is actually feeling the force 90 degrees downstream. You're pushing on it here, but then the rotated direction of this thing relative to this one, the rotated direction of this one is associated with this mass basically being pushed out to this point 90 degrees away, because it's basically feeling a continuous force which pushes it out into this new orbit. And then similarly on this side, it's being pushed down into essentially a lower orbit than this one. So instead of it going out like this way, what if it were just traveling in a tangential direction, and that direction, say, were this way, right? Because it'd be coming in and going into the board like that, you're pushing it a little bit that way so that it has a component not just of this motion, but of this motion. But this motion is actually on the disk, so it's not just coming straight out, it's on the disk. So that's what curves it out to this new position.